Many thanks to the organizers of this conference. So I'm going to talk about a recent paper that we have written with my colleagues Yves Colin de Verdière, who is in Grenoble, Maarten who is in Rice, in the US, and Charlotte Dietze, who is finishing her PhD between Munich, Paris, and other places. And the study, well, maybe it's a bit surprising to see a possible link between gas giant planets and Sub-Riemannian geometry. But the fact is that there is a link that I'm going to show. For those of you who have already attended my talk in Padua, so there will be a large common part, but you will see also a slight novelty. So the problem is the following. The problem comes from astronomy. And the fact is, so we are interested in the internal structure of gas giant planets in the solar system, so Jupiter and Saturn, typically. And in astronomy, it is widely conjectured and admitted that the interior of such planets is made of several layers. So the typical structure that is conjectured, again, but widely admitted, is that in those planets, in the interior of those planets, there is, as you can see above, a first layer made of hydrogen, of gas hydrogen. Then there is a second layer made of helium, called helium rain, because the helium, which is liquid, is falling in some sense by gravity. Then there should be a big layer, at least in Jupiter, for instance, of metallic hydrogen, which is liquid, fluid hydrogen, with a very high pressure. And then it is conjectured that at the core of the planet, there would be some ice rock, probably, but nobody knows. So this is the conjectured structure of layers that is thought by astronomers. And how can they measure something? So the fact is that inside those planets, there are some waves propagating, some acoustic waves. And the idea is to be able to measure those waves and to measure the resulting spectrum. And from the spectrum, I will show you how, we would like to be able to guess what is the structure. This is the topic of my talk. And the fact is that in gas giant planets, the speed of sound is isotropic, okay, or quasi-isotropic, but the speed of sound tends to zero as the wave approaches the boundary. This is in contrast with rocky planets, like on the Earth, because on the Earth, which is a rocky planet, right, fortunately, the speed of sound, when you have an acoustic wave propagating inside the planet, the speed of sound does not tend to zero when the wave is coming to the boundary. And so the wave crosses the surface, and we can hear it, we can measure it. It's not the case in gas giants, because the speed of sound tends to zero. So it means that acoustic waves are completely confined in the interior of the planets. Okay, so of course, then the basic question is how to observe such waves, because we cannot. We cannot unless we send a probe in the interior of the planet. And this is actually what was done a bit before. For instance, so this is the names Galileo, Juno, Cassini that you can see here. Galileo was a space mission. It was a probe which was active in the 90s, something like that. It was around Jupiter, around the moons of Jupiter, with some specific mission of observation. And at the end of the mission, so it was in 2003, the space agencies decided to dive the probe into the interior of the planet, just to measure, to see if it was possible to measure something. And it was indeed possible. I mean, so in 2003, Galileo dived into the planet. Well, not far, unfortunately, because it was disintegrated around 150 kilometers. So it was only a very, it remained more or less at the surface, of course, because of the pressure. And so very, very quickly, the contact with Galileo was lost, and the probe was probably destroyed very, very quickly. Anyway, there was time enough in order to measure already something and to guess that indeed there is some discrete spectrum inside. It was the first discovery. Then there was also, in the same way, Cassini. So Cassini was another space mission around Saturn and also the moons of Saturn. It was active around the years 2010. And astronomers decided exactly the same. So in 2017, Cassini was plunged into the interior of Saturn. But this time it was a complete failure because Cassini did not even reach the highest layer of Saturn. Because around Saturn there is already a small atmosphere which is very dense, and unfortunately Cassini was destroyed in this very small layer. So, well, nothing. And so the next one will probably be Juno. So Juno is currently active. It's a mission again around Jupiter. And probably, because it's not completely decided yet, they will decide to dive also Juno in September 2025 into the interior of Jupiter again. Okay, but so this is a basic way to observe acoustic modes, but probably not the best. And I'm coming to the fascinating part of physics, how to observe acoustic waves, because they remain confined in the interior of the planet. The fact is, and I would be completely unable to explain how and why, okay? So don't ask me. But the acoustic waves interact with gravity waves inside the planet. And then, okay, let us admit that acoustic modes create a kind of oscillation of gravity. And these oscillations of gravity imply small oscillations of the rings around the planets. So everybody knows that Saturn has big rings. Okay? Also Jupiter, actually. Jupiter has small rings too. And the small oscillations of gravity inside the planet imply small oscillations of the rings that you can measure. And from those observations, which are very fine and very delicate to do, you can imagine, you can then reconstruct by solving some inverse problems that I do not want to go into this delicate problem. They are able to reconstruct a part of the spectrum, a part of the discrete acoustic spectrum. So this is the physical motivation. Now let me come to the mathematical model about that. So I will be essentially at the blackboard. So let me, how it goes, like that. How can we model such a problem mathematically? Well, we will assume that the planet is a Riemannian manifold. Let us call it capital X with a metric G. So capital X is compact, smooth. Right? Let me assume also that the dimension of X is n plus 1. Of course, in the case of planets, you take n equal 2. You will see why. Locally, so it has a boundary. Okay, so capital X is a ball in our setting. And locally around the boundary, capital X is like, let's say, an interval 0, 1 times a manifold capital M. Let me put some coordinates. Let me call U the transverse coordinate and Y a coordinate on M. So M is a Riemannian manifold without boundary of dimension n this time. And now to model the fact that the propagation speed of the sound vanishes at the boundary, we will assume that G is a singular metric. It's singular at the boundary. And it is written, say, like, maybe I will write it here. Let us assume that G is written like G bar divided by U to some power alpha, where alpha is some positive real number which is which is assumed to range between 0 and 2. And G bar is a smooth metric. I mean, on X. I mean, smooth until you reach the boundary. So the degenerate metric, the fact that it degenerates is modeled by the U to the power alpha. And actually, it can be proved that there is a normal form near the boundary, which is like, so let me write the normal form. So G is like U power minus alpha times, where is it? du square plus some metric G0 at U. What I mean by G0 of U, G0 is a smooth metric, which is, you must understand, it is pulled back to the level set U equal constant. This is what it means. Okay, so this is the model. Here, as you can guess, alpha equals 0. The limit would be a pure Riemannian case, which is not singular. And alpha equal 2 corresponds to the hyperbolic limit. So certainly, this is why we think that it is in between, right? Now, first, so to analyze, what we are going to do, of course, is to analyze the Laplace-Beltrami operator and the spectrum of it. This is what we are able to reconstruct. And from the knowledge of the spectrum, at the end, we would be very glad to be able to guess what is the value of alpha. It would be great. So let me show how to do that.
In the last thing you wrote G0 of U,
oui.
It's not G0 of Y, it does not depend on Y.
No. What I mean, you're right. So G0 of U is a smooth metric, let's say, on the shift of M at the level set U. This is what it means. Okay.
How is the dependence on Y?
Smooth. Okay. So you are, this is a metric which is pulled back to the level set U equal constant. This is my notation. Okay. But then you are right. Of course, it also depends on the variable Y on M. Okay. Let me do two changes of variable. So two changes of variable in order to facilitate the study of the Laplace-Beltrami operator. The first is that instead of U, let me settle a new variable X, which is one-dimensional, so depending on U, which is just actually the integral of V to the power minus alpha over 2 dV which is up to constant. Let me ignore the constant, u to the power 1 minus alpha divided by 2, so that G is now dx square plus x to the power minus beta G1 of x, where again, G1 of x is a smooth metric pulled back to the level set x equal constant, right? And beta is 2 alpha divided by 2 minus alpha. So given that alpha is in between 0 and 2, beta is a priori any positive real number that we want to guess. And now with this writing for the metric G, the volume associated with G is x to the power minus beta n divided by 2 dx and times d vol G1. Okay, so this is the volume. And as you can already see here, the volume is finite if and only if beta is less than 2 over n. So you already see that the specific value of beta, which we call the critical value, 2 over n, will play a role, evidently, in the spectral study. And we will see that. Actually, by the way, we can notice that the Laplace-Beltrami operator is essentially self-adjoint if and only if beta is not less than 2 over n. It means that in that case, I don't have to make precise which Laplace-Beltrami operator we are considering. And actually, for the values of beta which are less than 2 over n, we will consider the Friedrich extension, right? So, okay. So, Dirichlet. Right. So, this is the first change of variable. The second change of variable that we do is different because maybe we are not so much happy with the fact that the volume is singular. Okay, so in the second change of variable or function, we are reducing the problem to the Lebesgue volume just by changing the function f to any function f you associate as a new function x to the power beta n divided by 4 f. Right? And so then you reduce the problem with the new volume form is dx d vol g, g1, and and now the local form of the Laplace-Beltrami operator is, and this is the main object of the talk now, minus dx square plus x to the beta Laplace-Beltrami on M plus a potential, a constant c divided by x square. It's an easy computation, of course. You make the change of function. You compute the new form of the Laplace operator. You find this guy with a c. I can give you c, but it's not important. Beta n divided by 4 times beta n divided by 4 plus 1. Okay. And by the way, you can already notice that, well, actually, you can completely ignore the potential because in what follows, it will have absolutely no impact on the spectrum. But anyway, there is a potential. You can already notice, anyway, that we will write this Laplace-Beltrami operator in the usual form that we like, a sum of square of vector fields. Okay, this part can be written like that, plus this potential, which will play no role. So it's a Hormander operator, and of course we know well how to manipulate this kind of potential, this kind of operator. So from now on, the game will be to compute, this is what we are going to do now, compute the Weyl for this Laplace-Beltrami operator. And at the end, the game will consist to analyze the real data which are provided by the astronomers to try to guess, if possible, the value of beta, at least this. Let us start with this. So I can show you the main result that we have, the main mathematical result that we have, and I'm going to prove it. It's not difficult. So our main result provides the Weyl law. So capital N of lambda is the Weyl counting function. I mean, you are given some positive value of lambda. For me, the eigenvalues of the Laplace operator are positive, right? So you consider the opposite of the Dirichlet Laplacian. And capital N of lambda, given a lambda, is the number of eigenvalues less than lambda. So the Weyl law gives an asymptotics of this function as lambda tends to plus infinity. And so what we have proved, and I'm going to sketch in one moment, it's not difficult, is that with constants that can be made completely explicit, I've not written the constants in my slides to keep them not so heavy, capital N of lambda is, except for the critical value of beta, it's a power of lambda. You see, it's not a surprise. For beta, which is less than the critical value, capital N of lambda has the same asymptotics as in the Riemannian case, meaning that for the subcritical case, you do not feel the singularity. So, the Weyl law does not feel the singularity. For the critical value, there is a logarithm, as it is now by now standard in the Grushin case, because I will come in one moment to the Grushin situation, Bawendy-Grushin. And for the supercritical case, which is certainly the one of interest, capital N of lambda is another power of lambda that I will show in one moment to be like the Hausdorff dimension. Hausdorff dimension divided by 2. And in turn, as a consequence also of our computations, we can have also a result on the concentration of the eigenfunctions near the boundary by computing what we have called in the past, many of you know, the Weyl measure. So what we prove in this second result is that as soon as you are in the critical or supercritical case, almost all eigenfunctions do concentrate at the boundary. I mean, the Weyl measure is a Dirac. It's a Dirac mass. Right. Maybe a comment on this result. The subcritical part of this result, I mean, for beta less than 2 over n, and maybe also the critical case, you will tell me, Dario, can be actually recovered from the paper, the recent paper by Yassine Chitour, Dario Prandi, and Luca Rizzi. It's contained. Their study allows to find this result, but not, correct me if I'm wrong, not in the supercritical situation. In the supercritical situation, your paper gives a double inequality, right? Right, but it does not give the equivalent. Okay. Yeah. And by the way, we are actually not completely sure that this result is completely new. So, well, but it's not the problem, right? I'm going now to show how to prove this result, and you will see it's not very much difficult, But it's unusual anyway, because we are not exactly in a sub-Riemannian situation. Let me come now to that point. So let me make a proof. Non, c'est pas ça. Voilà. Let me make a proof of it. A sketch of proof, actually, a proof in a particular case. The proof consists in applying the method that we have developed with Yves Colin de Verdière and Luc Hilleret in our paper on WeylÅs in Sub-Riemannian geometry that I have talked about many, many times in front of many of you. So let me take a simplified model for the vector fields here. So we have, let me come back to this writing. I is ranging between 0 and n. Okay, not 1. I start with 0 because I'm in dimension n plus 1. Okay? And so the local model is x0, which is d over dx, and xi, which is x to the power beta divided by 2, d over dy for I ranging from 1 to n. Right? So this is the basic model. Of course, it's not the exact model, right? I'm just making a simplification just to show you how it goes. Of course, you can recognize the celebrated Bawendi-Grushin case in dimension n plus 1, but the power on x is contrarily to what we are used. It's a real number, right? A positive real number. And so the usual techniques that we know well, Hörmander, Lie brackets, and so on, completely crash here. The vector fields are not smooth. So we cannot say, for instance, or I'm not able to say, I've asked many times the questions to experts, and once here again, would it be able to prove, for instance, it's an open question, I do not know, that delta is subelliptic in some sense? I don't know. I still do not know. It's an open question. It's an interesting open question. So it means that we won't rely on subellipticity. This is a big problem. All the techniques that we have in Sub-Riemannian geometry cannot apply. So we have to be careful. But anyway, let me show you that at least in this simplified situation, things are very easy to do. And there are not many problems. Indeed, such a case is homogeneous. In the usual case of Sub-Riemannian geometry, you introduce the usual dilation. And here the dilation is evident. You take delta epsilon of xy, which is by definition equal to epsilon x, and epsilon to the power 1 plus beta divided by 2y. Okay? The usual dilation of Sub-Riemannian geometry, except that the power is not an integer, but okay, it's not a big problem, right? Because, of course, you can check that the vector fields are homogeneous in the usual sense. I mean, if you multiply epsilon times the pullback of xi under the dilation delta epsilon, you find xi, right, for every I. And so from this basic homogeneity, and assuming that the heat kernel does exist for this kind of operator, but it's not much difficult, but it has to be checked because we are not in the standard situation. But there exists a heat kernel, okay, let us admit. A heat kernel that is a density, sorry. Then from this dilation, from this homogeneity property, you have the classical homogeneity property for the heat kernel, meaning that epsilon to the power n plus 1 plus beta n over 2 times the heat kernel. The heat kernel I will denote it by E. At time epsilon square t, the usual scaling, with delta epsilon of x, y, and delta epsilon of x prime, y prime, is exactly equal to E of t, x, y, x prime, y prime, right? Okay, and this is because we have a kind of flat case. Otherwise, we would have an expansion. But let me keep this very simplified situation where we have the exact homogeneity for the heat kernel. Now, what we are going to do in order to compute the Weyl law, as I said, we are going to follow the general method that we have done with Yves Colin de Verdière and Luc Hilleret. So we are going to apply heat kernel method, and the heat kernel method consists of estimating heat trace. I mean, so this is what we call local Weyl law. So what is a heat trace? I mean, you are taking a function, f, a smooth function or continuous function, an x, and you want to estimate the trace of the heat semi-group against the multiplication by f, right? That is something like an integral over capital X of the heat kernel along the diagonal f of q dq. dq because we are with the Lebesgue measure, right? So this is the object that we want to estimate as t tends to 0. And why do we want to estimate this guy? Well, this is because it can also be written as the sum of a j of exponential minus lambda j t, where the lambda j are the eigenvalues, times the integral of the phi j square f dq, where the phi j are some basis of eigenfunctions. And as soon as you know the small time asymptotics of that guy, you can apply a Tauberian theorem, Karamata-Tauberian theorem. That is, you take the inverse Laplace transform, and you can guess, then you can compute the Weyl law, among others. So this is the usual way. This is a very usual way. Now, how can it be done? You see, to compute a Weyl law with this method, with this heat kernel method, essentially what you need to know is the behavior of the heat kernel along the diagonal in small time. That's it. And this is why if you don't have any singularity in your problem, this is quite obvious because you just have to take, you know, the tangent space, the nilpotentization, right? And so you find the nilpotentized heat kernel and you are done. In the equiregular case of Sub-Riemannian geometry, computing this is very obvious. But it's not obvious, very far from obvious, in singular situation, near singular points. And precisely here, of course, we have, in the usual sense of Sub-Riemannian geometry, we have a singular situation, of course. This is the line x equals 0. So it means that we must expect this integral to be a singular integral. So we have to estimate a singular integral. That's it. That's the analysis that has to be done. And so let me show how it can be done. So let me take an f which is supported near the boundary, okay? And let me compute the integral I of t, which is the heat trace, which will be the integral near the boundary. So that is on the product, let's say, 0, 1 times minus 1, 1, n to the power n. Okay, I'm taking local coordinates of the heat kernel along the diagonal times a function f, which is locally supported, again, dx, dy. Okay, this is what we have to do. And so the way we are going to proceed, the variable y will actually play no role, because by Fubini, we will integrate at the end against y, and we will integrate over 0, 0, 1 e of t x. Oh, from now on, since we only manipulate the heat kernel along the diagonal, let me ignore the repetition of the variable. Okay? So for me, the notation e of t xy means along the diagonal. Okay? And also, since y is a parameter in a local chart, I can assume that y equals 0. Okay, so sorry for the ambiguity, but it is something like that. F of x 0 dx and dy. Right? Right. So now what we are going to do, it is, as I said, a singular integral because of the singularity, because okay. And so what we are going to do is split this integral. This is one of the main ideas in our big paper with Yves and Luc that we called J plus K decomposition. So you split this singular integral into two components, J and K, where where J of t will be by definition the integral between x equals 0 and x equal to square root of t, right? Of e of t x0 f of x dx. Let me completely ignore the rest of the integral because we can focus on this. And okay, so this is the first part. We cut it at x equals square root of t, and k is the rest. You see, we follow the natural scaling of the heat equation, of course, and k is the rest. That is the integral between square root of t and 1 of this integral. Okay. Now, to compute them, computing the asymptotics of G is easy. So for J, we make a change of variable. We set x equal to square root of t times u. And we get that J is equal to square root of t times integral between 0 and 1 of e of t and delta square root of t of x 0, let me write it like that, times f of delta square root of t of, oh sorry, this is a u, sorry, u of u 0 du. Right? We use the dilation. But now, thanks to the homogeneity of the heat kernel that I just cleaned. It was on the previous blackboard. This guy is equal to square root of t to the minus n plus 1 plus beta n divided by 2 e of 1 u0, right? And so we obtain exactly 1 divided by t to the power n over 2 plus beta n over 4, integral between 0 and 1 of e of 1 u0 times the f. And now I can make an approximation, because as time t is going to 0, this guy is continuous. So I can say that it is like f of 0, 0, right? Meaning that you have concentration at the boundary, exactly. And for this part, you have concentration at the boundary, right? So this is the small time asymptotic of j. It is 1 over some power of t times a constant, which is explicit in some sense. Okay, so this is j, and this is not difficult. Now the difficult part, the more difficult part, is computing k. How to compute k? Let me show you. K, let me rewrite k here, is integral between square root of t and 1 of e of t tau 0 f of tau 0 d tau. Okay, I have changed my variable. Now let me write it slightly differently. Let me write it, and this is the trick, actually. We make a kind of blow-up, of desingularization. We say that t is equal to tau square times t over tau square. Well, it's not so deep, okay? And we write it as delta tau of 1, 0. Okay? Delta tau of 1, 0 is exactly equal to tau 0 times f of tau. And now we use the homogeneity again here. We say that this guy, thanks to homogeneity of the heat kernel, is equal to tau to the power minus n plus 1 plus beta n over 2 times e of t over tau square 1, 0. Right? So let me maybe rewrite here, maybe in the middle. So k is integral between square root of t and 1 of 1 over tau to the power n plus 1 plus beta n over 2 times e of t over tau square 1, 0 times f of tau 0 d tau. Okay, but now you see it was a kind of desingularization. I will tell you why now. Because whatever the value of this s, this is an s equal t over tau square, you don't care. But this guy is taking the heat kernel at some time, but in the Riemannian zone, right? Well, again, along the diagonal. This means 1, 0, 1, 0 again. But we are inside capital X. We are in the Riemannian zone, right? Because now x equal 1. We are far from the boundary. We are far from the singularity. So this is a desingularization, exactly. But so there is no problem now, because since we are in the Riemannian situation, we perfectly know that this guy is like the usual Riemannian case. And the usual Riemannian case gives you tau square divided by t to the power, which is the topological dimension on the manifold, divided by 2, right? Times, I will not write, but times a smooth function of tau square divided by 2. Just because we are here in the Riemannian case. No problem. Let me ignore the smooth part, okay, which would give a complete expansion. I don't care. And so what you get is maybe up to some constant, okay? Constant. I do not want to compute the constant. It's painful. Divided by t to the power n plus 1 over 2. This t is coming from here, right? Of an integral between square root of t and 1 of 1 divided by tau to the power beta n over 2 times f of tau 0 d tau. Right? Okay, so you already, here you have, let's say, the usual asymptotics of the Riemannian case, but now it is multiplied by this term, of which we should compute the time asymptotics as t tends to 0. So it's now a simple exercise, of course, because you have to compute the asymptotics of this integral as t is tending to 0. So you see it depends on the value of beta n divided by 2, and that's all. Either the integral converges or not. Okay? So the final guess, the final computation gives you that this guy is equivalent to a constant divided by t to the power n over 2 times 1 plus beta over 2 times f of 0, 0 if beta is greater than the critical case, 2 over n. If beta is exactly equal to 2 over n, then you obtain a log. So you have a constant times the logarithm of t, or maybe with an absolute value, we don't care so much, divided by t to the power n plus 1 over 2 times f of 0, 0. And the last case, I would say, is the usual Riemannian case. If beta is less than 2 over n, it was the, the finite volume situation, the usual case. Then in that case, you find that it is equal to a constant divided by t to the power n plus 1 over 2 times integral over 0 and 1 of tau to some power minus beta n divided by 2 f of tau 0 d tau. So we can, this computation gives you exactly the result above. Let me, oui?
Where did you use the first extreme of the integration, the square root of t, and not any other function of t or even 0?
I don't see where, sorry?
So remember in the definition of k, you were integrating only between square root of t and 1.
Right.
Why there was this choice?
It comes from the scaling. The square root of t is due to the usual time scaling of the heat equation.
But you didn't use it.
No,
We need 0.
it's hidden. It's much, much hidden here, actually. The fact is that, well, to say it shaking the hands, for small values of tau, which it's not on the blackboard anymore, but for tau less than square root of t, it means that essentially the nilpotentization wins, to say it in another way. For tau a bit too large, and too large means larger than square root of t, It does not win anymore. The nilpotentization, it's like in the talk of Omar. Exactly. It cannot win. You have many tangent spaces in some sense. That's the idea. So you have to desingularize in the sense of Hironaka. And so here it's very basic, no problem. But here you see you have only one bifurcation in some sense, which is at tau equals square root of t. And for this part, this is a trick in some sense, you see. And with this trick, you throw things far from the boundary. This is the usual blow up in desingularization, you see. And once you are in the regular zone, then you know the asymptotics. Or maybe, if you want to be more rigorous, if you do not want to use this well-known situation, you can here nilpotentize again. It works. Here you use the nilpotentization, which gives you exactly this power. Okay? And so here is, so you see this final result is indeed in accordance with the result I showed on my slide. It gives you this now by applying the Tauberian theorem, the inverse Laplace transform. Moreover, you also see the concentration for beta, which is critical or supercritical. You see that only the value of f at x equals 0 is kept, which exactly means that you have concentration on the boundary. While in the subcritical case, you have to keep all the values of f. This is the standard Riemannian situation, and this is why also I'm going quickly, but you get the usual Weil measure of the Riemannian case, which is the Riemannian volume. Okay, so this is the proof, and you see that the proof is not difficult. No, not difficult. It's much more difficult in a general j'ai vu. In a general singular situations. So let me show you now some numerical data. I will not show you the numerical data. No. It's a big Excel file, horrible. And out of it, by making many numerical computations that are not much interesting, we can estimate, this is done last week only. So this is my novelty with respect to Padua. We can estimate the Weil law, and you have here a kind of curve of capital N of lambda, not for very high values of lambda, not for the moment, because computations are ongoing. They are done by astronomers in the US, in the MIT. But from those first guesses, it's very clear, and we are very happy with that. It's very, very clear that we are in the supercritical situation, this for sure. And the first rough estimate is that beta should be something like more than 2, maybe 2.3, something like that, which is far beyond the supercritical case, because much beyond the critical case, because for planets, we have n equal 2. So the critical case is beta equal 1. So we are much beyond. And why is it so much interesting to be in the supercritical case? Because from the Weil law, we can indeed reconstruct the value of beta, right? Otherwise it's not clear. Otherwise, the first term in the Weil law is not enough to reconstruct the value of beta. Maybe we would need a higher order term, maybe in the local Weil law. We don't know. For the moment, we have this first result, and we are happy. It's a good news for us that Jupiter and Saturn are supercritical, because we can reconstruct beta. Right, and so let me maybe say one word to end. I don't have time to write some perspectives, but there are quite many perspectives out of that work, also concerning, for instance, classical questions in quantum chaos like quantum ergodicity. Can we get quantum in the supercritical case, can we get quantum ergodicity at the boundary? It's not clear. It's not clear again because we are with a non-smooth case. So we don't even know if the limits measured are invariant under the geodesic flow over M, which is the boundary. We don't even know how to prove that because we don't have the usual smooth tools. So we don't even know. And there are other problems also. I will end with that. With observability. Of course, it's very tempting to write for this kind of problem observability inequalities, of course. And so, for instance, is it provable that probably under geometric control condition, GCC plus maybe something else, would we have observability inequalities? Okay? So I will end with that, and I thank you very much.
Thanks, Emmanuel. So we have time for, let's say, at least one quick question, possibly two.
So I have one question about the proof of your theorem. So when the Laplace is not, so you used that the heat kernel is homogeneous. When it's not very nice and very doesn't satisfy it, because here it's essentially the group. What do you do in that case?
So actually, I cheated. I cheated for the talk. I cheated doubly. So how would we do if the heat kernel is not homogeneous? Then we would hope to have a complete expansion, okay, like in the classical case. And then we would be able, in principle, to write a full expansion of the J and the K as t tends to 0. It would be a first answer. But this result, having a complete expansion of the heat kernel, we have it in the Sub-Riemannian case. We don't have it here. At least we do not know how to prove. So actually, and this is why I cheated for the needs of the talk, in the paper we do not do like that. We first prove, well, there are several things to prove, but for instance, one technical thing that has to be proved is that you can localize the heat kernel. You know, the Katz principle. You do not feel the boundary. You do not feel what is far from you with the heat kernel. We have to prove that. So we have to establish, to say it in mathematical words, you should prove that outside of the diagonal, the heat kernel is exponentially decreasing. And once again, here you do not have the classical results. You do not have. So it's a first thing that has to be proved. So in the paper we did a method, but a few days ago actually we found another method which is more convincing in my opinion. We apply the Kanai transform, transmutation. We write the heat kernel as a transform against the wave kernel. And then we use the finite speed propagation for the wave kernel. Again, it has to be proved, but it's not difficult. Because you can approximate, as it was done in a talk, maybe in the talk by Valentina this morning, you can approximate by a usual Riemannian case, and from that you can get easily the finite propagation speed for the wave equation. And then with the usual trick that was developed by Chigger, Gromov, and Taylor, you can get quite easily exponential estimates for the heat kernel. And then all the machinery can be done.
Thank you.
Just a question about the model. Is it clear that coding the velocity of propagation of the sound in the Riemannian metric is the right way? Or you would need more, I don't know, a diffusion coefficient in front of the Laplacian, something like that?
Yeah.
Is it obvious?
No, it's a very good question. Our model is very rough. I mean, it's just a first one. Actually, we also made another. So what is quite clear is that we have a singular Riemannian metric, because it seems to be the only way to stand for the fact that the sound of speed vanishes at the surface. Okay? So this is the first observation. Now, what is not at all clear is that in our model, we took beta, or alpha before, we took beta to be a constant. But why? You see? Why? Maybe beta is variable. Maybe beta varies as a function of x and y. And in that case, okay, we really do not know. We really do not know how to establish a Weyl law in the case where beta is variable. It's a completely new question, actually. Even, as I said at the beginning, I was stuck during maybe 2 months on trying to show subellipticity here with, with a boundary pseudo-differential calculus. Boundary in the sense of Melrose, so can you imagine? So it's difficult. And I asked to experts in Hanover, in particular, last September, and they were surprised by the difficulty of this, however simple case. It's strange. It's very strange.
Thank you. So if there is no other question, we can thank Emmanuel again.